Hi, so let's restart our lecture about new unit. This time we are going to begin a whole new unit of Mdof model. This is also the last unit we're going to practice in this lecture, and it is based on all the knowledge we learned until right now. Okay, so until right now we learned that if there is a earthquake moving like this, or structure M and K will fall into this direction, deformate in this direction, and all the motion equations happens to here. However, in the most of case, we cannot use this single degree freedom solving every problems. A more popular problem or more useful model is MDOF model. Is for example, for the case of building structure, we consider each floor as one mass, and there are columns and frame stiffness as the floor stiffness like this, and consider this kind of structure model. Or in the case that for building structure, for bridge structure, we consider the footing, the pile, the pier, the girder, as multiple mass and multiple springs, and a lot of also base springs, something like this. I'm very similar with this model. So from today we're going to talk about this kind of model and how to solve this kind of problem. Okay, as MF single degree freedom, firstly we consider that the structure is moving to this direction and the earthquake moving. So once they moved to a new position like this, a little bit chain thing in the spring here, but you can understand that this is the deformation of the spring, right? So the movement of the ground, we say, is y0 in that direction, this direction, right? The x direction in the inverse direction, we call this direction for the structure is the positive direction. Okay, it's just inverse with earthquake direction. Please notice that. The same with the single degree freedom, and to the ground, until the ground to the ground, the deformation of all the mass is x1, x2, x3. So this length from here to here, from original position to here, is x3, x2, x1. Okay. So their global deformation, global displacement is Z3, Z2, Z1, which is x1 minus y1, right? In that direction, if we consider. Okay, so we consider this mark for this vector x1, x2, x3. For y is a unit vector. All the elements have the same value of y0. So z is z1, z3, z2, z3, and we can say that is equal to y minus x minus my y minus, because that 1 is equals to y0 minus x1, that 2 is y0 minus x2, and that 3 is y0 minus x3. So due to this kind of model, we can also consider that the differential equation also, if we take the differential, it also becomes like this, and 2 times differential means acceleration also becoming like this vector equations. Okay, thus we can say that if we multiply m to each of them, they will become the r. So what is r here? R is the restoring force that acting on all the mass due to the structural deformation. So how to calculate them? So this is R3, R2, R1. If in the middle floor, for this floor, there are 2 forces acting on the mass, right? For the mass I, to have a mass mi, and you have Ri, that is equals to the equals to the force in that direction in the underfloor and the force on the other side of the floor spring, right? Upper floor force. Because for one floor, there are one shear force in that direction, then there will be a symmetry force on the other side acting on inside the spring, right? On the inside the column or the frame. So this is why the force in here is positive, the force in here is negative. So it's Fi minus Fi plus 1 if I is smaller than n. So what is in the top floor? If we see it in the top floor, the Fn is equal to the Rn. So Rn is equals to Fn that under it. So because the n plus 1 floor is the air, no force here, so it's Fn equals Rn. Okay, so what is the spring force here? The spring force, we know that the spring stiffness we know K1, K2, K3. So we only need to calculate the deformation of each floor drift or floor deformation. So then we can calculate the spring force, right? So what is U1, U2, U3? How to calculate U1, U2, U3? U1, U2, U3 is like this. Not until here is only this part. U3 is only this part, right? So how to calculate them? We can calculate them like using this equation, or we can rewrite them like this: K1, K2, K3. This is also called as local stiffness. So for U1, for the first floor, each U1 is equal to X1, right? These two are the same. However, for the floor that upper than it, UI should become the floor's displacement. This floor displacement minus this floor's displacement, right? We will calculate their relative displacement. Only the first floor is the same one, right? So if I larger than 1, then ui equals to xi minus 1, right? So for 1, that ui equals x1. So we already know that ri equals fi minus fi plus 1 for the case that I is larger than 1 and also smaller than n. Then we know that they are equals to ki ui minus ki plus 1 ui plus 1, because this is this one, right? So more furtherly, we know ui is xi minus x minus 1. Ui plus 1 is xi plus 1 minus xi, right? Because the equation of the deformation of each floor is look like this, because I is larger than 1, right? Okay, so we collect all the xi minus 1 here is minus ki. All the terms that about xi here, xi ki plus ki plus 1 here. And I plus 1 here is minus ki plus 1, like this. So for the case of I equals to n, top floor, we know that Rn equals to Fn, and that is equal to Kn Un, and Un equals Un minus Xn minus 1, right? So we know that is in top floor is minus Kn Xn minus 1 plus Kn Xn. Last case, I equals to 1. So we know the I1 is equal to F1 minus F2, and K1, U1, K2, U2 is come from here to here, here to here. And U1 we know is X1, U2 is X2 minus X1. So we get this equation X1, K1 plus K2, X2 multiple minus K2. So if we see these three equations together and collect them like this one, we can see a total matrix equation like this. For the case n equals I equals to 1, that we have this equation, K1 plus K2 minus K2. For the case that is larger than 1, smaller than n, that is minus K minus Ki, right? Ki plus 1 minus Ki, something like this. For the last case, for n case, we know that minus n Kn, something like this. So by these three equations, by this rule, we can calculate the matrix of K by the each floor stiffness K1, K2, K3, right? Okay. So for the equations of motion, we can get M1 matrix like this, M1 matrix like this, and this side will be the restoring force K R, which is K multiple X, and this side is the acceleration multiple the mass matrix. We can get things like this by moving this term to the left side of the equation. So mx 2 dot is equal plus kx equals to m y 2 dot. This is the equation that with earthquake input, but without damping, right? A more simple case is that without earthquake input, without damping, which is the free vibration case. Okay, and we can also have the free vibration with damping equation like this, no input earthquakes. Okay, and we will explain these equations later, so you can get more understanding of the multiple degree freedom. However, the final equation will be with earthquake input and with damping, right? And we are solving these equations for the assignment 5. Okay, so I think some of you already know that we can decide C by the eigenvalue analysis of MK matrix, and we can solve this problem by the modal analysis. But in here, we can tell you how to solve this problem by the time history integration, and then so we can do it for nonlinear case. Okay, this is all for today's contents.